Okay, so we've gotten through all of the preliminary work for multivariate functions, and we're finally going to step into a partial derivative. So we're going to learn how to take a derivative with respect to each of the variables in a multivariate function. The derivatives, let's say we're going to look at this at first in R2. This could be expanded to any Rn. But in R2, if you have a function f(x,y) that's differentiable at the point xy, you get two partial derivatives. You get a partial derivative with respect to x, which is the limit as h approaches 0 of f of x plus hy minus f of xy all over h. And then we get a y partial derivative, f of xy, which is going to be the limit as h approaches 0 of f of xy plus h minus f of xy all over h. Okay, so if you're looking at what's going on here, you're basically in the x partial, you're freezing y as a constant, and you're looking at how the value of f changes, only as how the value of x changes. And then in the y partial, you're freezing x as a constant, and you're looking at how f changes only as y changes. Now, unfortunately, because this is used in calculus and it's used in partial differential equations, and these things are used by physicists and all sorts of scientists, the notation here gets a little funky. All of these things mean the same thing. Okay, so all of these notations actually say the same thing. So f with respect to x of xy is the same as f with respect to x, is the same as the partial of f with respect to x, which is the same as the partial with respect to x of f of xy, which is the same as the partial of z with respect to x, the same as the first partial of f, or the first derivative of f, or the derivative with respect to x of f. All of these are equivalent. Likewise, we get the same notational difference when we look at y. So this can get a little bit confusing, but when you see any of these notations, they are all exactly the same thing. Okay, so let's look at a couple of examples to see how this plays out in practice. So let's take the multivariate equation f of xy is x cubed plus x squared y cubed minus 2y squared. So if I take the partial with respect to x, I treat x like a variable and y as though it's a constant. So I'm going to get 3x squared plus 2xy cubed, and then this is just going to go to 0 because there's no x part. Okay, so like if I took that value at, let's say, the point 2, 1, right, that's going to give me 3 times 4 plus 2 times 2 times 1. Let's see, that's 8 plus 4. No, that's a 3. That's 12 plus 4, which is 16. Okay, so that's 16. That means that if I'm at the point 2, 1 in the xy plane, so like down here I'm at the point 2, 1, that means that on the surface, when I'm moving in the positive x direction, if I move 1 unit in the positive x direction, f is going to move up by 16 units. So this thing's actually kind of steep in the x direction. Okay, so let's say that I take the same thing, but now I'm going to take the derivative with respect to y. So I'm looking at the original function, I'm going to take the derivative with respect to y. That's a constant, so that goes to 0. This is going to give me 3x squared y squared minus 4y. So if I take that at 2, 1, right, that's going to give me 3 times 4 times 1 minus 4 times 1. So that's going to give me 8. So if I'm moving in the positive y direction, f is only moving up by 8. So it's going up much steeper in the x direction than it is in the y direction. Let's take a look at an example that uses the chain rule here. So let's say I have f of xy is sine of x over 1 plus y. All right, so if I take this with respect to x, sine goes to cosine. We leave what's inside alone. And then with respect to x, that's just going to give me 1 over 1 plus y, so that's pretty simple. Let's take the partial with respect to y. Sine again goes to cosine. What's inside stays there. The x comes along for the ride. Let's see, it's going to become negative though. 1 plus y squared in the bottom. And let's see, the derivative of that's inside just 1. That's it. So there's your partial with respect to x, your partial with respect to y, and using the chain rule to do it.